So we want to give a more complete analysis of the situation. And as usual, if you want to do a more complete analysis, you need to go deeper into the mathematics. So that's what we want to do now. Instead of 682, let me just call it n so that I don't have to keep writing that number over and over again. So n is the number of stickers. And we saw that the expected number of stickers I need to buy is basically n times 1 plus 1 over 2 plus 1 over 3 up to 1 over n. This looks a little bit different maybe, but when n is 682, I get 682 over 682 plus 682 over 681, dot, 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 up to 682 over 1. Mathematicians love a sum like this. What do we do with this? When we have a function that you add its value at 1, at 2, at 3, and so on, there's a nice picture that we like to draw. I'll draw it over here. Here's 0, 1, 2. And now what I'm going to do is that I'm going to say, okay, let me look at this sum right here. I'm going to interpret it geometrically. Okay, so I want to say, okay, 1 is the area of a 1 by 1 square. So let me just go ahead and do that. That's a 1 by 1 square, right? This is height 1. 1/2 is the area of a 1 by 1/2 square. So let's go to half of this. And now this little piece is 1/2. Okay? 1/3 is going to be, now if I put a height of 1/3 over here, like this, and so on. So these little rectangles get smaller and smaller. And I keep doing this, and you can imagine that I keep doing this all the way up to n, where I'm going to get some tiny rectangle right here. Okay? And so this green thing right here is going to be the area of all of these rectangles together. Okay? Let's put another one right here. Now, there's a really cool thing about this, which is that if I look at these points, they make a very nice shape. You see that? They make this very nice curve that I'm going to fill in. So this is a very beautiful curve because when x is equal to 1, the height is 1. When x is equal to 2, the height is 1/2. When x is equal to 3, the height is 1/3. And so this has a very nice name. This is just the curve y equals 1 over x, right? And if you look at these green rectangles and the area that they form, they're not too far from this area under the red curve. Let me divide by n. N over n is equal to this thing. And I want to say that it's almost the area of this red shape. So this sum over here is equal to the sum of the areas of these green rectangles. And that's very close to this red shape, but there's some stuff that's missing, right? It's this, and this, and this, and so on. But now, look at these purple pieces. What's the total area of those purple pieces? Actually, if you can imagine taking them all and just shoving them inside this square, let me try to draw a picture of that. So here's a square. I'm going to draw it a little bit bigger. Then these purple shapes fit nicely like this. You see they all fit neatly into this square. And actually, if you look at each one of them, it's almost a diagonal. So, you know, this is almost a triangle, which is almost half of the area of this rectangle, and so on. And so I'm going to kind of eyeball that this purple area is definitely less than 1. It's definitely more than 1/2. I think it's maybe a little bit more than 1/2. Okay? And so we know more or less how much this area is. This is about 1/2. We'll say something a little bit more precise, but definitely we're going for hand wavy for the moment. I'm just trying to get an estimate for how big this is. And really the main reason for that is that actually the bulk of the area is in the red. And this stuff is actually pretty little, we're about to see. The thing about the area under a curve is that this is one of the most beautiful things in mathematics. This is one of the reasons calculus was invented. If you're familiar with this, you know what to do. And if you're not familiar, I'm just going to write the expression and assure you that this is something that you would do in a calculus class. So the area under this curve is basically going to be the integral starting at 1, ending at n, and the function is 1 over x. Now, how much is this? Well, the integral of 1 over x is the logarithm of x, and this goes between x equals 1 and x equals n. And then we'll say this is still about a half. I guess I should say this is approximately equal. Okay? And if you look at what this is log n minus log 1, and then plus a half. Now, one of the properties of logarithm is that the logarithm of 1 is 0. And so you see, the point is that this 1/2 almost doesn't matter because as n grows, log n is much bigger. Okay? But so what we get is that the number of stickers that we need is about the number of stickers that we want. This is 682 times some penalty for the repetitiveness of stickers. I find this absolutely fascinating that the penalty is exactly the logarithm of n plus a constant. Why should the logarithm of n come up here? And by the way, this is the logarithm in base e. This is the natural logarithm. And I think it's really beautiful that that's what comes up. That's the penalty of filling the Panini album of 682 stickers is about the logarithm of 682. That's where that number 1,000 comes from. Let me state a more precise version of this theorem. N is approximately n times the logarithm of n. And I kind of made this constant here 1/2. It turns out to be a little bit bigger than that, and it has a name. It's called gamma. This is called the Euler-Mascheroni constant, and it's about 0.577. So this is not too far from the estimate. And if you want to prove this, you need a little bit more calculus. But I think our estimate shows us that this is pretty reasonable.
Apart from one guy, that is the world record for memorizing pi. So someone recited, what is that now? We're over 125 yards of pi. Someone memorized all the way up to here and couldn't be bothered to remember the next 0.